Now, in general, absolute max or absolute min are not easy to find because they don't necessarily even exist. For instance, look at the function inverse tangent of x on the entire x number line. This does not possess an absolute max or absolute min. In fact, it has two horizontal asymptotes. So let me jar your memory if you've forgotten. The inverse tangent has two horizontal asymptotes. And so the y values never even touch the y value of pi over 2, yet it does keep increasing and increasing and increasing. Okay, so the function here is the inverse tangent of x, and it goes something like that. All right, and notice it never touches those horizontal asymptotes, so there is no absolute max, no absolute min. Now, this was an open interval from negative infinity to infinity. However, what if the function was more constrained? What if you're analyzing this on a closed interval? So in other words, if we close this off, would the function have an absolute max or absolute min if you closed it off with brackets? And the answer is yes. And this theorem is known as the extreme value theorem. If f is a continuous function on a closed interval, a, b, then f has an absolute maximum, f of c, and an absolute minimum, f of d, for some c and d in this closed interval, a, b. So this is a very special case in which we could analyze for a maximum or minimum, not only any maximum or minimum, it's an absolute max and an absolute min. And so here is the procedure for doing that. We're more concerned about differentiable functions. We want to take advantage of the first derivative as a tool. So here's the first step, second step, and third step. All right. So we're going to be analyzing mostly differentiable functions. Let's go ahead and find the absolute max and absolute min for the following function. Notice this function does not have any domain issues on this closed interval. Okay, closed, remember the bracket means you could include -1 and include 8. So the endpoints are included in the function values. So we'll go ahead and do step 1. First thing is to find critical numbers. So procedure 1 or step 1, we need to find critical numbers, type 1 and type 2. And we're just going to do the product rule here. And we want to take advantage of our algebra. Look for the greatest common factor. Greatest common factor here is going to be 1/3 x to the -1/3, and this will give us some really, really neat stuff. And if your first derivative is a fraction, make sure it's in reduced factored form. And that will allow you to analyze and find critical numbers much quicker. I forgot a 3 here. I need a 3 right there. Now it's factored correctly. All right, we're ready to find type 1 critical numbers. Type 1 critical number says set the first derivative equal to 0, and then you're analyzing the numerator. And so we get C is equal to 4/5. Now let's look for a type 2 critical number. Type 2 critical number says when does the first derivative does not exist. Okay, when the first derivative does not exist, you end up solving this equation. And notice we get C to be 0 here. I meant to write the letter C earlier. Now I'm going to go ahead and relabel my two types of critical numbers. I'm going to order them according to the number line. So I'm going to call C sub 1 to be 0 and C sub 2 equals 4/5. Now step 2 says we will analyze the output values. And we need to evaluate the function at these critical numbers. And notice the function evaluated at 4/5 is not a very big number. It's a portion of 6/5. The portion of 6/5. In fact, I know it's less than or equal to 6/5 because this fraction here, or this number here, is less than 1. So it's going to be a portion or a proportion of 6/5, but this fraction right here, this first one, this first fraction right here, you could see that that's going to be less than 1. Now we need to evaluate the endpoints. So we need to evaluate f of -1, right? Remember, a is -1, b is equal to 8. We got to evaluate the endpoints. And the other one is f of 8. Cube root of 8 is 2. 2 squared is 4. And now we simply compare all these outputs. We compare all these numbers and see which one is the biggest. The biggest number here is 3. Okay, so therefore, at x equals -1, absolute max of the function is is 3. Now the other endpoint at x equals 8, absolute min is -24. And so notice there are multiple steps here in order to look at local max and local mins, or absolute max and absolute min from the extreme value theorem. Let's look at another example where we could find the absolute max and an absolute min for a continuous function on a closed interval. Notice for this function, there are no domain issues on the entire set of real numbers. So it's certainly continuous on this interval here. The function is also differentiable. So we're going to take advantage of the first derivative to find critical numbers. We're going to go ahead and use the quotient rule. And we want to simplify this. We want to put this in reduced factored form. And let's make the numerator a little bit friendlier, along with the denominator. And we're ready to find our type 1 and type 2 critical numbers. Type 1 critical numbers occur when the first derivative is equal to 0. So you simply substitute the first derivative to be 0, and then solve for the letter C. Remember, for this, the exponential function can never actually equal 0, so we're left with just solving this. So type 1 critical number is C equals 2. Let's go ahead and find type 2 critical numbers. Type 2 critical numbers occur when the first derivative does not exist. So we end up trying to solve this equation, and there's no real solution here. So there is no type 2 critical number. We only have a type 1 critical number. We're ready to proceed to step 2, which is to evaluate the function f at the critical numbers. In this case, we only have one of them. That's 2 over e. And if you're wondering how much that is, that's about 2 over 2.7. That's about 2/3. Let's evaluate at the endpoints. So we got to evaluate f of -2. And then f of 4. And that's about 4 over 7.4. And we're ready to state our conclusions. So our last step here, or our last procedure, we want to say something like, at c equals 2, the absolute max for the function is 2 over e. We also want to say at x equals -2, the absolute min is opposite of 2 times e. And so there we go. We were able to find the absolute min and the absolute max for a continuous function on a closed interval.